Okay, so thanks for coming. So today we have Lindon Roberts. So he's from ANU. He's a fellow at the Mathematical Science Institute over there in Canberra. And he's going to talk about derivative-free optimization methods. And I just read in his biography that the paper was voted the best paper, got the best paper award in 2019, which is pretty exciting. And apparently the software is available as well for this new algorithm. So very exciting. Thanks for coming, and it's all yours. I'm going to mute myself as well.
Okay. Okay. The recording's started, I assume.
Yes, I think it's Vera because I can't.
Okay, great. Okay, I'll get started then. Well, thanks for having me, and thanks in particular to Amandine for organising and for Vera for the invitation. Yeah, so I'm going to talk about some work I've done over the last few years on derivative-free optimization for least squares problems. I'm not expecting you've heard of derivative-free optimization, so I'm going to make sure that we cover that as well. As Amandine said, feel free to jump in with any questions, but yes, this is joint work with Cora Cartus, who's at Oxford, so that was sort of my main collaborator for this work. Also, Jan Fiala and Ben Marteau, who are at NAG, so the Numerical Algorithms Group, who some of you might know, they're a sort of a software company based in the UK. And so some of the work, in fact, most of the software I'm going to talk about is available in the commercial NAG library right now, as well as being available open source. And I'm going to talk about a couple of applications at the end. Hopefully I'll have enough time. First one is in climate, which is work with Simon Tett in Edinburgh. And the second one is on image learning variational regularization parameters for imaging, which is work with Matthias Erhardt at Bath. So some of this work was supported by EPSRC in the UK and NAG as well, which is why that's sort of incorporated into some of their commercial libraries. Okay, so let's get started. So the plan today is that I'm first going to give everyone a bit of a background into what derivative-free optimization, which I'm going to call DFO, is, under the assumption that you only have sort of limited experience with optimization as well, just to make sure that no one's sort of left behind on this. And I'm then going to talk about how we kind of specialize that to parameter fitting problems in the sort of context of nonlinear least squares problems. And I'll talk a bit about what we do from a software perspective to try and kind of make these algorithms work a little bit better in practice. And hopefully I have a bit of time at the end to talk about the two applications I mentioned, which is tuning climate models and learning image denoising parameters. So we'll see how that goes for timing. Okay, so let's get started with derivative-free optimization. So the context I'm going to be looking at here is going to be essentially nonlinear, non-convex optimization. So we've got some objective function f, which is just going to map Rn to R, and we want to find a minimum. That's sort of it. You know, as I'm sure many of you know, this is common across all sorts of application areas, but is very, very non-trivial to solve in sort of efficient ways, numerically speaking. Within this, obviously, there's quite a lot of variety in so the sorts of assumptions you can make about the problem. And what I'm working in the context of is where we have essentially no information about the structure of the objective. I'm going to assume that it's smooth, so that finding a minimum is in some sense a sensible thing to do. So continuity, differentiability, this sort of thing. But I'm not going to assume anything about, for instance, known problem constants. So things like if I happen to know any bounds on the derivatives or anything like that, I'm not going to assume I have access to any of that information. And I'm potentially going to worry about the situation where we can't even evaluate f accurately. So imagine something where f has some kind of stochastic calculation underlying it. Maybe there's a Monte Carlo simulation or something like that, so you can't get out the true solution, or that perhaps there's some iterative process underlying the calculation of f. So something that in theory you'd run off to infinitely many iterations, but you truncated it at some finite number based on some termination. And in that case, you don't have an exact solution either. So it's potentially going to allow these sorts of situations as well. I'm only going to talk about unconstrained optimization because this is the first case that we really want to be able to solve well before we tackle sort of the trickier problem of with constraints. But in all the software implementations, we just allow simple bound constraints on the variables. And I'm going to go even further and say that we're not going to look for the global minimum of f, so not a point that is smaller than, so an f of x star, that where f of x star is smaller than f of x for all x, but just a local minimizer where it's the smallest in a neighborhood. And in fact, because optimization tends to be a very difficult problem, we, in a lot of cases, will jump from, well, in theory, you might want a global minimum. We're only going to maybe be able to get you a local minimum, but actually, realistically, the sorts of algorithms I'm going to be talking about really will only give you an approximate stationary point. So it's a fair bit weaker, but in practice, this is sort of a very commonplace thing that we do, and it seems to work very well in the goal of finding a local minimizer in practice. And this is not specific to the work that I'm talking about. This is true more generally in nonlinear optimization. And one phenomenon, particularly for those of you in sort of numerical analysis, but perhaps in other areas, something that I find sort of somewhat specific to this sort of area is that there's a more substantive gap between the sorts of algorithms you might be able to prove theorems about, the sort of algorithms you might have in a textbook, and the sorts of things that work really, really well in practice with state-of-the-art performance, compared to things, for instance, like finite element methods or maybe PDE type problems. I get the impression that there's a much larger gap between what things we can sort of write down simply and what things work really, really well in practice. And I think that's probably in some sense related to just the difficulty of the problem, the generality of the problem that we're trying to solve. So hopefully I'm going to spend a bit of time talking about some of the ways that I sort of address this gap as well, but I obviously won't have time to talk about all the details. Okay, so under the assumption that maybe you don't have much experience with nonlinear optimization, I'll just give you a very quick background into an approach for nonlinear optimization. And what we're going to do here is we're going to take the objective function f, and we're going to assume that we have access to some point xk in the kth iteration, where we're hoping that our xk's will approach a minimum in some way. So the way we approach this iterative process is that given our current base point, we'll approximate our objective with a local model. So this is why I'm writing m sub k. And in this case, you can take it to be anything that you hope approximates the function well locally, so around xk. And in this case, I can take it to just be a second order Taylor series, for instance. We tend to find that quadratic is sort of the most commonly used level of approximation in practice in terms of a balance between sort of effectiveness of the algorithm and the complexity of manipulating the model. So typically we'll approximate the objective locally with a Taylor series, a quadratic Taylor series, and then we can simply go, well, let's not minimize f, let's minimize our approximation to f. So we'll do that by setting the gradient of m to 0. And if you do that, you get the famous Newton's method, where at each iteration you take your xk and you move it by a step sk, where sk solves this linear system here. So Hessian times s is minus the gradient, which is the stationary point of that local approximation. So as I've written here, one of the first drawbacks that you'll come across very quickly is that this method may not converge. There's a couple of reasons for this, the most notable being that this linear system that you're trying to solve might be singular. There's no reason that your Hessian matrix should be invertible at any point. So you may not actually be able to find an S that satisfies that linear system. Or potentially you could have, if your Hessian is not positive definite, then you have no guarantees that moving in the direction S will actually decrease your function, and you could be finding a maximizer of the model rather than a minimizer. So you could end up being stuck in a maximum rather than a minimum. So as written there, it's a very simple method, and it often works fairly well if you're very close to a solution, but in general, it won't converge for any function for any starting point. And so there's a lot of work to try and ensure global convergence, so some sort of convergence guarantee regardless of where you are. And one approach that is the sort of flavor that I tend to work with is where you restrict the step size. So what you do is you say, instead of just finding a stationary point of m, you try and find a genuine minimizer rather than a stationary point. but you impose the constraint that you can't take too large a step. So this is working under the basis that your Taylor series approximation is only really accurate for small steps. So let's maintain some measure delta k of what we consider a sensible step size where we think our model is accurate, and we'll minimize our model subject to that constraint. And this is a very specialized type of problem. This constraint defines a region that's called the trust region. This problem that I've written here, minimize a quadratic model subject to this trust region constraint, is called the trust region subproblem. And this is a very well-studied family of algorithms. Minimizing a quadratic, non-convex quadratic function subject to a Euclidean ball constraint is a well-studied problem, and there are specialized algorithms to solve that problem, either to full optimality or to get approximate solutions to that. So we can efficiently calculate the step sk via this method. If we then stick it into sort of a full algorithm, this is roughly how we might do it. So given a current point and a current trust region radius, so delta k measuring how accurate we think our model is, we'll evaluate f and its derivatives to construct our Taylor series approximation. We'll solve this subproblem to calculate a step sk. Then what we do is we evaluate the objective at our new point, and we measure how good this new point is. And to do that, we calculate the ratio of the actual decrease in the function versus what we predicted the decrease in the function would be according to our model. And based on this ratio rho, we'll make a decision about what we do in our algorithm. So if rho is large, so something like at least 0.7, then we'll say this step was very good. We got a good decrease compared to what we were hoping. So we'll accept the step and we'll move to our new point, and we'll increase our trust region radius because things are going well. So we might as well take larger steps because our model has shown itself to be fairly accurate. In the middle case, where we did decrease our function, but perhaps not by as much as we would like, we consider this a successful iteration still because we did get a good decrease in the objective. So we'll move to our step, but we're not confident maybe that our model is super accurate. So we won't take larger steps in the future. So we'll keep delta the same size as it was before. And if things are going badly, where we got a very small decrease in our function, or perhaps rho is negative and we increased our function value rather than decreased, then we'll consider that unsuccessful. We won't change where we are, and we'll shrink the size of our trust region radius in the hope that that'll make our model more accurate, because as we know, if you shrink the region, the Taylor series should become more accurate. And that's the basic flavor of the algorithm. It's well studied, and the sorts of theory that you get around it look something like in the limit, the gradient of your iterates goes to 0 or something like that. Are the sorts of theoretical guarantees you might end up with. So if we look into this a little bit more, the key underlying basis here of the whole algorithm is that we can locally approximate our function with a Taylor series, or by some other mechanism that's sort of some local convex, some local quadratic approximation. So if we do it, say, with this Taylor series, we've got to calculate the gradient of f and the Hessian of f at our current point xk at every iteration. So how might we go about doing that? Well, that's fairly straightforward to do. If you know what f is, you know the analytic expression of it, well, you can just differentiate it yourself and write a piece of code that evaluates that derivative. If you don't, or you're lazy, you could do something like finite differencing, and so just perturb the points and numerically approximate your first and second derivatives. Or you could even do things like algorithmic differentiation. For those of you that haven't come across that, that essentially is a sort of a software package that you can sort of put on top of your code for evaluating f, and it essentially breaks up the source code of your evaluation of f, and essentially uses the chain rule to construct code routines for the analytic derivatives of f. But that does require sort of quite substantial access to the code that evaluates f. So there are some limitations around it, but it can be a very effective tool when it's used. For people with some experience in machine learning, the backpropagation algorithm for things like neural networks is an example of algorithmic differentiation. So these are all very good tools and we use them all the time, but there are some situations where it's not really applicable. So if your function is black box, so there's some routines that you don't have the analytic expressions for, you perhaps don't have access to the source code, maybe there's some proprietary code, maybe it involves someone physically going out and doing an experiment. Either way, you don't really have sort of the full breakdown of f, then you can't write down the derivatives by hand, and you wouldn't be able to use algorithmic differentiation packages. if your F has some kind of noise in the evaluation, then even in what sense you can get accurate derivatives could be pretty much impractical, essentially, to estimate derivatives accurately. And if F is computationally expensive, then the cost of doing something like finite differencing or algorithmic differentiation might be very, very high and sort of not practical for you to do. So in these sorts of settings, this is where people will turn to derivative-free optimization, DFO. So there's a lot of settings where this sort of arises. Hopefully I'll get some time to talk about two at the end. But things like finance, where you've got Monte Carlo models, climate I'm going to talk about later, where you've got very expensive and noisy simulations. People have also applied to various design problems, again, where you've got maybe large-scale simulations used to evaluate the design of whatever it is that you're building, or experimental design. And this is what I was talking about, where the evaluation of F involves someone going out and doing an actual experiment in the world. And in no reasonable sense can you differentiate someone's lab experiment. So these are the sorts of contexts that DFO might arise, as well as many others. So now I'm just going to give a brief idea of how we adapt sort of classical optimization methods into a DFO type context. There are many different flavors of DFO algorithms. I'm going to talk about a category called model-based, in the sense, and it's model-based in the sense that we do construct a model and it really tries to mimic what works really well for derivative-based optimization. So these sorts of, the algorithms I was talking about just before, things like Newton's method, are very effective in practice when you have derivatives. So let's try and take as many of those features as we can get. And that's the sort of flavor that I work with. But some of you may be familiar with the Nelder-Mead method. There's also a large family of algorithms called pattern search or direct search. There's genetic algorithms. There's many, many different flavors. But I'm only going to talk about one of them here. And so the way we do it is we want to use basically the framework we had before. So before we had a local approximation of our objective by a quadratic Taylor series. So what I'm going to do is replace the gradient of the objective with some vector G and replace the Hessian of F with some matrix H. And I'm just going to say, let's find a G and an H in some way without using derivatives of the objective. And then I've got my quadratic approximation and we can carry on as we did before. So how do we do that? Well, to do that, we will interpolate over a set of points. So we'll maintain a cloud of interpolation points and we'll fit a function to these sort of well-spaced points sitting in Rn. And we'll use that to replace, and we'll fit a quadratic function for these points, and that'll replace the Taylor series approximation. But we hope that it's a broadly similar level of accuracy. But once we've done that, we now have a model and we can plug it into a trust region approach, as I mentioned just before. So the sort of people that did a lot of work early on with this, people like Andy Conn at IBM, Mike Powell, who's at Cambridge, who some of you might know, Katja Scheinberg, who's now at Cornell, Philippe Toine Namur in Belgium, Luis Vicente, who's now in Lehigh in the US. So what does this look like as a picture? So let's suppose I'm trying to minimize the blue objective and find the red local minimum point. And I'm starting from this large black point in the middle. And I've got a particular trust region, which is the ball around my current point. So that's this shaded region, so xk plus or minus delta. And so let's start by constructing an interpolation set. So I've evaluated my function at 3 points in black. And that because that's the number of points you need to fit a quadratic in one dimension. So I can fit my quadratic to those 3 points and I get this line in black, which is a fairly good approximation to the objective. So now what I can do is I can minimize the objective inside this region. Well, obviously that gives me the point on the right-hand side. So I can evaluate that point and measure how well I did. And this was a good point, so I want to add it to my interpolation set. Well, that'll mean I have 4 points in my interpolation set to build a quadratic function, which doesn't make sense. So what I'm going to do is add this new point in and delete an old point by some mechanism. In this case, I'm just picking the point that's furthest away. But there are better ways to do it in practice. So if I do that, I end up with a new model. I've changed my trust region radius based on the standard updating methods. And now I've got a new interpolation model and I can repeat. I can minimize it, delete a point, and I'm slowly progressing towards a solution. So after a couple of iterations, I've got an approximation that is very accurate for the objective in the neighborhood of the minimum. And so if I minimize that objective, I pretty much hit the true solution. And I'm essentially done. Okay, so let's talk about some of the theoretical aspects of these algorithms. So the key thing that we need to think about here that we didn't need to think about in the classical setting is the geometry of the points. So if your interpolation points have a good geometry, then you can prove, and I'll state it slightly more carefully in a second, you can prove that your interpolation model has the same accuracy as a first order Taylor series. And in the sense that the approximation to the objective goes something like the trust region radius squared, and the error in the gradient approximation goes like the size of the trust region. But this means that we have this extra caveat if the geometry of our points is good. So we need to modify our algorithm in a way that it'll make sure that the geometry doesn't get bad. So if it's bad, then we need to be able to fix the geometry in some way. However, if we do that, then we can get the sorts of results that we would get in a derivative-based setting. And the results all pretty much look the same. There are some constants that tend to be a little bit worse, but the basic flavor looks the same. So we get global convergence to stationary points. So the gradient of f at our iterates goes to 0. And we can also prove things like a worst case complexity bound, which says that we need approximately epsilon to the -2 iterations before we can guarantee that we've seen a point where the gradient of f is at least as small as epsilon. So you get exactly the same result in derivative-based or derivative-free settings here. Okay, so if we have a look at what this geometry requirement is in a little more detail, what we do is we suppose that our interpolation set is y0 to yp, so some collection of points in Rn, and we'll usually I tend to make the convention that the first point is your current iterate, and then we build our model by imposing that our model interpolates the function at that point for all our interpolation points. Well, what we can do is we can build the Lagrange polynomials for each of our collection of interpolation points. And these are going to be the polynomials where if you evaluate them at your interpolation points, all of them evaluate to 0 except for one, which evaluates to 1. So you have as many Lagrange polynomials as you have interpolation points. And essentially the key idea is that you have good geometry if your Lagrange polynomials are small. And roughly speaking, you can think about that as the interpolation problem in the sense you could write as a linear system, for instance, is well conditioned. And so the key theorem that we need for these sorts of algorithms goes like this. If your Lagrange polynomials are uniformly bounded inside your trust region, and all your interpolation points are either within the trust region or close to it, so the distance between your interpolation point and your iterate is at least bounded by a constant times your trust region radius, then your interpolation model is fully linear. So that's why I said before, in the sense that it's as accurate as a Taylor series up to constants throughout the trust region. And that means we're essentially done. If you've got something that's as accurate as a Taylor series in the region that we care about, then we're essentially going to get the same results as we would in a classical derivative-based setting. And it turns out there are some fairly simple algorithms to both check whether these conditions hold, and if they're not hold, how do we change some interpolation points to make sure they do hold. But I'm not going to talk about those. And so if we put it all together, this is the sort of algorithm that we have. So now, given a base point and a trust region radius, we're now going to add an interpolation step. We're going to construct our interpolation model MK by just fitting a quadratic function to our points. We can then solve the trust region subproblem, so minimize the quadratic inside the trust region, evaluate the point, measure how well we did, and we can, if we're doing well, we add the point. If we did badly, we don't accept the step. So all these updates are exactly the same. There's only a few changes that we need to make, which I've highlighted in red. So if things are going well, we'll add our interpolation point to our new iterate, sorry, xk plus 1, to our interpolation set, because we want to incorporate that when we build our model in the next iteration. If things are not going well, so our rho k is small, then we make two decisions. We check, is our model Taylor series accurate? Were our Lagrange polynomials small? If it was, that's the last unsuccessful case. So our model was accurate, but our step was bad, in which case we should shrink the trust region radius. If, and this is the third case I put in here, if our step was bad, but our model was not accurate, well, then what we need to do is stay where we are, keep everything the same, but make our model accurate first. So we don't want to unnecessarily call a step bad, call it unsuccessful, unless we know that actually the model wasn't the problem and it was the region that we were approximating the function over. So we now need to make this little distinction. But essentially, there's a couple of things I can't quite fit on in here, but this is essentially how these algorithms end up working. Right, so that's sort of a very quick introduction to at least the model-based flavor of DFO. So now let's have a look at how we can adapt it to least squares problems. I realize I'm running a bit short time, so hopefully this won't take too long. So what I'm going to do now is specialize to a particular class of objective functions. So now instead of just f of x, I'm going to say f of x can be written as the 2 norm of the square of a 2 norm of a residual vector r in Rm, or the sum of squares of the components of R. And so firstly, if we're in a classical setting, we've got a little bit of extra structure. So what we'll do is replace a quadratic approximation for f with what works quite well, it tends to be a linear approximation for R. And so if we take the Jacobian matrix of first derivatives of R, then we can get this linear Taylor series approximation. And if you break that down, that actually corresponds to making a particular approximation for the Hessian, which works particularly well if your if the components of R are close to 0, or if the function R is close to linear. So this is what we do in the classical Gauss-Newton method, and this works quite well in practice. So now let's have a look at what we could do in the derivative-free setting. Well, in that case, we don't have access to a Jacobian, but what we can do is take this linear Taylor series approximation that we made for R and replace it with a linear interpolation model for R. Exactly the same way as we replaced a quadratic Taylor series for F with a quadratic interpolation model for F a couple of minutes ago. So we maintain an interpolation set and we use that to find J, and then we've got a linear model for R. And in that case, we then take the natural, in both cases, classical Gauss-Newton and derivative-free Gauss-Newton, we can use a model for the trust region subproblem, so a model for F that is just the sum of squares of our model M, because M is approximating R, so if we just take the sum of squares, we get the square of a linear function, so we get a quadratic model that approximates F, and it's a simplified quadratic model in the sense of this approximation that I've written on the left-hand side here. Okay. So that's the classic Gauss-Newton method and how we adapt it to the derivative-free setting. So I will note that we're not the first people to look at least squares problems in this derivative-free context, but what previously have been done is to really build quadratic models for this function R. So in the same way that we build quadratic models for F, in the general case, building quadratic models for each component of R. And that works fairly well, but we've found a few advantages of taking linear models. So the first thing is that all the theoretical results carry over the same as before. But we have the advantage that we don't need as many evaluations of R to build our first model. So we have to start by sampling some points to build up our initial interpolation set. So we don't need as many because we're only constructing linear approximations rather than quadratic. And because we're only doing linear interpolation rather than quadratic, that's a much simpler problem. And it turns out that that leads to the cost of building these models is at least 7 times faster than the quadratic case. And that essentially means that they're more scalable. So we can solve larger scale interpolation models, which essentially means that we can solve larger scale optimization problems with the same sort of computational cost. And a nice little point that people that are more interested in numerical linear algebra might care about is that we get a more explicit connection between the geometry of our interpolation points and sort of linear algebraic quantities. And I'll briefly describe it here. So in this algorithm, we calculate a new point xk plus 1, and we add it to our set by deleting some existing points. So in my little demonstration, I just deleted the furthest point. But in practice, what we'll do is we'll delete a point that has a large absolute value of the Lagrange polynomial. That's sort of the standard way, and you can think about that in the sense of this geometry measure that I was talking about earlier. So it turns out that for linear models, changing one interpolation point gives us a rank 1 update of the linear system corresponding to this interpolation. So if we call that matrix A, and we've got a rank 1 update to A, well, that induces a rank 1 update in the inverse of A by the Sherman-Morrison formula. And it ends up looking something like this. So you get a rank 1 perturbation UV transpose with a constant term 1 over sigma coming in. And it turns out when you do this in the linear case, actually this sigma is exactly the value of the Lagrange polynomial the teeth Lagrange polynomial, the point you're deleting, evaluated at your new interpolation point. So there's a very explicit connection. You can see if your Lagrange polynomial is large, then your sigma is going to be large, and you're going to avoid sort of a large blow up in your inverse. So there's a very explicit connection that you get there. Okay, so that's how we do things algorithmically, and just a few little quirks with the linear models and things we can get out of it. Don't have a huge amount of time, so I'll mention briefly a couple of things we do in the software. So the software package that we've got, we call DFOLS, so derivative-free optimization for least squares. It's in Python, and it does least squares with bound constraints. It's on NAG's GitHub page, which is there. There's a few things that it does that lead to sort of some useful benefits in practice. First being that it's fairly flexible in its model construction, in the sense of how many interpolation points it can use an arbitrary number of interpolation points to build the model. We also have a multiple restarts mechanism that makes it very robust to objectives that have noise in their evaluations. And we've also got a mechanism for very expensive objectives where you can make some progress from 2 evaluations, rather than in general for an n-dimensional problem, you'll need n+1 evaluations of your objective before you can start making any progress. So we can bring that down to 2 for very expensive evaluations. However, we don't turn this on by default because in general, it's if you can wait, then you should, is the sort of lesson that I won't have time to talk about here. So for the flexible model construction, I won't talk about it too much, but basically, we now replace n+1 interpolation points with p+1 interpolation points. And then we find the linear model that minimizes this sum of squares of residuals. So this reduces to sort of a rectangular linear system for the interpolation problem. So if this is square, if we have n+1 interpolation points, then we have standard linear interpolation over R, and we just invert linear system. If we have fewer or smaller than n+1 interpolation points, then we can either build a linear least squares problem, which gives us a regression model, which can be useful if you've got noise in your evaluations, because linear regression is going to be a bit better than linear interpolation when you have inaccuracies. Or for the reduced initialization cost, if you have not as enough points, then we'll select the minimal norm solution with some modifications. But what I'll very quickly mention is to look at noisy problems. So over the course of these algorithms, the trust region radius delta goes to 0. There's a theorem that will tell us that that's what happens. So what this means is that our interpolation points will get close together as we go, because the distance between them should be of size delta. Problem is, if we've got noise in our objectives, then that means that the objective values of all our interpolation points are going to get closer and closer together. But if we've got noise in them, that means that all the values are essentially going to be within noise level of each other. And so when we build an interpolation model, we're really only going to be capturing noise in the objective rather than any genuine signal. And this is a problem because that means we get an inaccurate model and things don't work well. But actually, this is one of the main use cases we had for DFO in the first place. So to show you what happens, this is a plot of a particular run of DFOLS on a function where I've polluted it with some stochastic noise on its evaluations. And now I'm measuring the decrease in the objective in a normalized way. So it should go down to 0 on the left-hand axis, so down to -infinity on the log scale. And so it should go off the bottom of the screen, but it flatlines over time as the algorithm progresses at some non-solution. So it stagnates at some incorrect location. And if we look at more closely at what it's doing, is on the right-hand side, I've got a plot of the trust region radius delta in red, which does go to 0 as we expect. And in blue, I'm plotting the change in the model measured by the change in this approximate Jacobian across iterations. And so what we see is that we get some stuff happening at the beginning, but in this region where it stagnates, after about 20 on the x-axis or maybe 30, what we see is a very clear trend. Our trust region radius just goes straight to 0, which is our indicator that things aren't going well. We're getting a lot of unsuccessful steps. And our model is changing a lot between iterations. In fact, the change in the model between iterations is only getting bigger and bigger. And this is what I'm calling stagnation. So all our points have got to within some noise level of each other. And so now our interpolation model is just capturing noise. And so it doesn't produce a good step, it produces an unsuccessful step. We reduce our trust region radius and our interpolation points are even closer together. which means our model fluctuates massively when we incorporate new information because it's just fitting to this stochastic noise. And essentially we get an increasing rate in the change of our model because it's only interpolating to noise, and our trust region radius goes to 0 because things aren't working. And we get this stagnation phenomenon. So there's a few ways people have proposed of dealing with this, essentially revolving around the natural things of doing averaging. So you evaluate your function multiple times at the same point to reduce the noise, or by doing regression. So you sample very heavily in your region, and then you can hopefully average out that noise, and DFLS captures both of those. But what we have proposed is this multiple restarts mechanism that I mentioned. And what happens here is that when our trust region radius gets small, we say we're probably only going to be capturing noise from now on. It's hit some sort of not very useful level. So what we do is we reset our trust region radius to a much larger value. We update our interpolation set, we fix it up so that it looks good inside this bigger trust region, and we progress from there. The idea being that we don't just try to approximate in this local neighborhood where we've only got some noise. We expand our region, and over that region, we hope that there's some genuine signal that we can capture and we can keep making progress. And we also have a little mechanism to detect that stagnation more quickly based on essentially looking at these plots I had before. The trust region radius is going to 0, and the change in the model is going up fairly consistently. Then we'll also call a restart as well. And so if I look at exactly the same problem with the same random noise as I showed you before, but now we do restarts, I'm showing those with the lines in black. What we get is very quickly, we don't stagnate at the point we did before, but we can keep decreasing our function value to the level that actually we're essentially solved it up to noise levels. So here we see the red and the blue line, so the noisy value and the true value have sort of diverged. So we've essentially solved it up to the accuracy that we might be able to expect. So I won't talk too much about this, but if we compare this restarts mechanism by measuring the proportion of my test problems that I've chosen here solved versus objective evaluations, we find this restarts mechanism basically outperforms other techniques, particularly things like averaging and regression, in the sense that it's just as robust. It can solve as many problems as averaging and regression does, but it doesn't suffer from this penalty of potentially needing very many evaluations, particularly in the early stages of the algorithm. So it's not unnecessarily evaluating the objective. So that works quite well in practice. So this seems like we don't have theory to back it up like you do with averaging and regression, but this seems like a very effective heuristic in practice that balances robustness with performance in the early phase of the algorithm. Okay, so I've only got a couple of minutes left, so I won't mention how we do the reduced initialization cost. You can ask me about that at the end if you want. I want to very quickly talk about some of these applications. So the first one is parameter tuning for climate. So these are global models of atmospheric physics that we're looking at, and we want to tune them by fitting them to particular sort of global observations, things like global average temperature or humidity, these sorts of things. And the reason that people can't use sort of standard off-the-shelf parameter fitting sort of least squares tools is that we have two of these cases I spoke about for the why you would need DFO. So simulations are expensive because these are global climate simulations, and they're noisy, corresponding to the fact that we have a chaotic underlying physical system. So if you take 2 points that are near to each other and you run them forward in time, you potentially end up with fairly different outcomes. So in that sense, something like finite differencing is not really reasonable, and they don't have access to adjoints either. So what people do right now is what I consider sort of a manual tuning process. So what they do is they essentially, and not quite randomly, but almost randomly, generate a whole bunch of combinations of parameters, and they basically just evaluate and pick the ones that are the best. It's a little more sophisticated than that, but it's not massively different. And so we propose instead to use DFOLS with the multiple restarts mechanism, instead to have some actual optimization going on rather than essentially sort of guesswork, roughly speaking. And so if we do this, this is the number of evaluations. So this is to fit 14 parameters to an atmospheric physics model. I was given 90 evaluations of the objective, and this is measuring the progress under some specific cost function. And generally, from the climate people, something under 5 is considered a good fit. So it sort of matches the observations to within a desired tolerance. And we see we can get that very quickly. And actually, by adding multiple restarts, we can improve the progress we make a fair bit as well, which is, again, the dark lines in black there. So we ran DFOLS from a few different starting choices for parameters, and they all converged to 5 different local minima, all of which fit the data. And we've done some analysis, and we're fairly confident we've actually found 5 genuinely different local minima of our parameter fitting landscape, which is a potential problem. So it outperforms existing solvers, but actually we've now got a landscape where there's potentially multiple combinations of parameters that fit the data. So the question from a climatology perspective is, are these local minima different, and how are they different in the sense of what the predictions it makes about the world? And the interesting answer is that they give very similar predictions. They're not very different, these local minima. And the key conclusion here is that actually the uncertainty in the predictions of climate models, we've got different models calibrated to different data with different parameter choices, giving very different predictions. You know, if we look at what's out there in the literature, actually we think that the uncertainty of these is really going to be driven by the modeling choices, so what physical processes we include, and not the tuning of the parameters, so what you choose to fit to and so on, and how you choose to do that fit. I see I'm basically out of time, so I won't maybe talk too much about image deblurring, but basically we do image deblurring by some sort of convex optimization problem. The problem is this is an inverse problem, so we need to choose some form of regularization, and often these regularization, there's some uncertainty in how you choose it. So you might have some unknown parameters that weigh up your priors versus your data fidelity term. And so the question is, how do you choose those priors? Well, basically, you have to kind of just try a few values and see which one seems to work well. So the proposal here is to replace that with learning from data. So we're going to have a whole bunch of noisy problems and their true denoised values, and then we'll solve a fitting problem where we pick our regularization parameters, and then we minimize the fit that we predict from our denoising against the true solution that we have. So this is sort of learning the parameters from a collection of example test images. So we end up with this least squares problem where we've got these x hats come from solving a denoising problem, a convex optimization problem. In practice, this can be quite difficult to do because you then need the gradient of x hat, the solution to an optimization problem with respect to a particular choice of parameters in your problem. And you can do this with the inverse function theorem, but actually you need very high accuracy solutions to your denoising problem all the way through as you solve this bi-level optimization problem. And so what we've done is we've modified DFOLS to allow dynamic accuracy on its evaluation. So in the sense that DFOLS asks, please evaluate my objective, in this case, essentially evaluate x hat, to within some prescribed error tolerance that DFOLS selects, and that tolerance will decrease as you converge to the solution. So you start off with inaccurate evaluations, and then you increase the accuracy that you ask for as the algorithm progresses. But that's really probably the subject of an entire seminar at some point. So basically what I want to sum up with is derivative-free optimization is really useful when you've got objectives that are particularly expensive or noisy. However, if you do have access to derivatives, you probably should use them, is a general lesson that you should have here. We can adapt it to least squares problems. We can make them robust to noise with restarts. We can reduce their initialization cost, and they work well on some fairly important practical problems. A few things I'm looking at the moment are improving the scalability with things like dimensionality reduction techniques. I'm trying to improve some local convergence rates, so just improving the set of theoretical results available, and looking at more general objective problems, and maybe looking at constrained problems, because that at the moment is a fairly understudied area. That was everything I wanted to mention. I realize I've gone a couple of minutes over, but thank you for listening, and I'm happy to take questions.
Thank you. Thanks, that was great. I love the application for climate models. Do you know if your method is used routinely already for climate models, or they still try to assess if it's,
it's not at the moment. I think, so the paper that we've written on this, we only submitted a couple of months ago, so it's not kind of really out there yet. But so Simon and Edinburgh had done work with Cora, who I worked with on this, earlier, we're looking at not using this sort of derivative-free methods, but some simpler techniques, and was able to get some benefits there as well. We've shown that these methods are more sophisticated and do work better, and they are more robust, but I don't think it's really caught on yet.
Okay.
But perhaps some of this work that shows that actually the targets that you're trying to fit to, so the data you're trying to fit to, and which local minimum you end up at doesn't really affect the outcome of your sort of interpretation of what happens. It might give people a bit more confidence that they can use these sort of automated tuning methods.
Yeah, it's very interesting. I'll keep an eye on that. Is there any questions? So please go down to participants, and then you have the whole list, and you can raise your hands. Just the bottom button on the bottom. Yes, Jeff?
Thanks for a good talk. I was wondering how
sensitive your algorithm is to the various parameters involved. So like the 0.7 and the 0.1 and the step sizes or the minimum delta. So like how much of an art is it? And then if it is difficult to use, is it possible to use your algorithm to choose those parameters?
Okay,
so
that is
running another optimization where the
Yes.
thing optimizes the difficulty of doing optimization.
That's a very good question. So there's sort of two questions there. The first thing is sensitivity to these algorithm parameters. So there is some. It's not, and I've not got, so this simplified method I've chosen was the 0.1 and 0.7 and doubling and halving the radius sizes and so on. That's not quite what I do in the code. I do something a little more sophisticated. This is sort of the simplest I can write down that still meets all the standards of convergence theory. But there is still some sensitivity to all these sorts of things. We try to choose some sensible defaults that seem to work well in practice, but obviously for any given problem, there's probably a better choice than the defaults out there. So the second thing you mentioned of tuning the algorithm parameters is actually something that the DFO people have been aware of. I know of at least one piece of DFO software that does tune itself. You can give it here's 10 test problems, find me a set of good algorithm parameters that work well for these. And yeah, there is some work on just in general using DFO to tune algorithms. So like this imaging problem that I mentioned as well, which is essentially an algorithm tuning, parameter tuning problem. So yes, you can do it. I don't, I try and just choose some sensible defaults and go from there. But yes, there's nothing stopping you from doing this. Although there is the question around what your measure is. So how do you pick, what do you consider a better choice of algorithm parameters? If it did better on half your test problems and worse on half, how do you say this parameter combination was better than that parameter combination? And that is a little nuanced, and it's not straightforward how to do that. But once you've decided on something, yes, you can definitely do that.
I suppose
That's
I was
good question.
Of trying to do it just for one problem
at a time. So as you perhaps run the problem itself, it's tuning itself for that only problem.
Oh, so dynamically on the fly. So that's sort of a bit of a trickier one, because yeah, I'm not sure there's a clear way of doing that within a single run of an algorithm. If you allow the algorithm to run to completion several times, you can assess what's better or worse. But actually the way that this is sort of done, let me go back to one of these examples. Where are we here? So really what we're doing with this, particularly the changes in delta, is a level of dynamism that we've got. If you look at algorithms, it seems to be more common in convex optimization. They assume that you know things like bounds on your derivatives, and then they say the equivalent of going always use delta equals this value that depends on some problem constants. So this is already to some extent dynamic in the sense that it chooses how well you can approximate your function dynamically based on how things are going, rather than on knowing problem information. So already it's got sort of that flavor that you're talking about, but this 2.5 and 0.1 and 0.7 you can tune, but I think you really need multiple runs of the algorithm to be able to assess it. So that may or may not be a sensible thing depending on the application, and it is very problem dependent what the best values are. So we just try and pick good defaults and hope for the best.
Okay, is there any other question? We have a couple of minutes. Yes, Matthew, please.
Hi, Lyndon. Thanks for your talk. I have a question. You mentioned that you there's some other work where they use the quadratic model for this function r inside the norm.
Yeah.
And you replace it with a linear model. I would have thought that the linear model was the obvious first thing to try, not the quadratic model. So I wonder if you could comment on the reasons why the quadratic model was done first. Is it something to do with convergence theory, or like, yeah, just curious why that it happened in that order?
Yes, that is a good question, and so it's hard for me to say. So I mean, I've spoken to a couple of people involved with these works, and I think there's sort of two motivations. So the first work, Zancone and Scheinberg, I think a key reason that they did it is that they, from a software perspective, they took a piece of code that Mike Powell wrote about 10 years ago now, a little bit earlier, and modified it for the least squares case. I'm not sure if any of you have had the pleasure of coming across Mike's code, but it's very, very, very good and very, very, very incomprehensible. So I think that was built on quadratic models for a general objective problem, and I suspect part of the motivation was we want to get this really good code working in the least squares case, but we don't want to have to basically rip it to shreds because it's so complicated. We just want to do kind of a minimal change to that piece of code to make it working, in which case we need to be able to build quadratic models. So I think there's a sort of pragmatic reason there, and then there's maybe a more sort of idealistic reason, let's say, where really the more information you can retain, so quadratic rather than linear, is generally considered a good idea in DFO. The underlying assumption is that information is hard to come by, so evaluations of the objective. So let's try and retain as much information as we can and essentially try and build the most complicated models that we can do. Because if we do more computation work in that, then that's nothing compared to the cost of getting more evaluations in. So in that principle, quadratic makes more sense than linear. But we were looking at it going, well, actually, you only need to consider some sort of medium-sized problems before actually the extra cost of all this quadratic interpolation rather than linear does actually start to impact you in a noticeable way. And you also get the benefit of fewer initialization evaluations, which is really good for simple problems that don't require many iterations to solve. But actually, we just find in general that because we have so much problem structure, the difference between quadratic and linear in the sorts of regimes that you look at DFO where you're not solving to super high accuracy, actually you don't see that much of a difference. Quadratic is more accurate, and if we're looking at very high accuracy, it does tend to be better. If you've got noise, it does tend to be a little bit better. But for the sorts of regimes that we care about, and particularly once we've got this sort of restarts type mechanisms as well, actually we find for the sorts of problems that we care about in the settings that we care about, it's not that different. But that's not obvious. I can definitely see how quadratic became the first thing to go with if you're coming at it from a DFO perspective rather than from a classical least squares perspective where linear is sort of the natural choice. Yeah.
Okay, thanks. And does that mean that the assumptions that you need to prove convergence in the linear model versus quadratic case are, how do they compare?
They're very similar actually, because really they're based around this full linearity concept, which I had back here. So this everything is as in a first order Taylor series approximation. So actually for the quadratic part, essentially because you don't want to capture all the quadratic information because then you've got n squared evaluations that you need to use. If you just capture a bit of the quadratic information, what you have to do from a theoretical perspective is just assume that your quadratic stuff is bounded, and then it essentially doesn't enter into the convergence theory at all. And then it's all really about how accurate your gradients are. So actually, theoretically, it's the same.
Okay, thank you. I think we have to stop here. Well, thank you, Lindon. This is going to be awkward, the clapping. But great presentation, and thanks everyone for attending. Thanks.
Well, thanks for having me, everyone. And yeah, feel free to send me an email or anything like that if you do want to talk more as well.
Yes, and if you want a recording of this session, we should have 1.5. So please email me or Vera or Lindon. And if you wish to present your work, please contact me. It would be great. I think we've seen that it's working pretty well. So yeah, please contact me, or if you have ideas of other speakers. And that's it for today. Thanks again.
Great, thank you.
Welcome.
Thanks.
Okay, thanks a lot.
Bye.
Bye.
Bye.